in listen-only mode.
Well, good afternoon, everyone, and welcome to the fourth in our Gen Less series of webinars. Today, we're joined by Marcus Baker of Apricus, and Marcus is going to talk about sustainable heating and hot water systems. So again, very much on the low carbon sustainability theme that we've been working with throughout this Gen Less series. Just a little bit of housekeeping from me. We had a chat with Marcus just before we switch the on button on, and Marcus would like to take questions at the end of the session, please. The way we'll run that is that I'll keep monitoring them as they come in, and then once we get to the question and answer session, I'll open up the microphones of individual questioners so that you can ask your questions in person. So please, if you wish to submit a question, there's a couple of ways you can do that. Either type it in to the questions dialog box that you should see on the right hand side of your screen, or you have the opportunity to raise your hand. But please, if you do raise your hand, don't necessarily expect an immediate response, because again, we'll have to monitor that remotely, and we'll be keeping an eye on it. But ideally, we'll take those questions towards the end, if that's all right with the audience. You are defaulted to closed microphones at the moment. That's to avoid feedback issues and background noise, which we do sometimes get with quite a lot of attendees. We had 118 registrations for this session today, so we're expecting and hoping most of that 118 will turn up. So yeah, you are all on mute, and as I said, I will unmute you to ask your question in person once we get to the time. So I think that's enough from me in terms of housekeeping. Please enjoy the webinar, and I'll hand you over to Marcus to talk about sustainable heating and hot water systems. Awesome. Over to you, Marcus.
Thank you. Kia ora, everybody. I assume you can see my screen fine, Mike, so therefore everyone should be able to see it.
Yeah, that's all coming through fine.
Wonderful. So we've got quite a bit to cover, so I'm going to fire straight into it. Just a little bit of background about who Apricus NZ Eco Energy are. We're the designers of renewable central heating and hot water systems, and we design and distribute for a few companies. The Apricus name comes from evacuated tube solar hot water systems. We also do a CO2 hot water heat pump called Reclaim. We have the EECA wood pellet boilers and EasyPel wood pellet boilers, both from Austria. So the first topic to cover off is solar hot water. And solar hot water is good for domestic hot water and process heating. There's a very small opportunity for heating, but it's not really that relevant. And just a bit of overview, I guess really this covers all the topics, but we are looking at a climate in crisis. And so the latest understanding and a declaration from the climate scientists last November was that climate crisis has arrived and it's accelerating. And it's pretty severe, and we're threatening ecosystems. Now, it seems quite bizarre, really, talking in this way after the COVID-19 experience that we've just been through and well, continuing to go through. And I think it probably gives us a bit of insight into what accelerating can mean and what severe can mean, and fate, etc. So some just emotions and thoughts to dwell on as we try to unpack how we can mitigate and evolve. And you can see in the background, in February we had some flooding and we had a bit of drought as well, all at the same time. And the recommendations are 6 pointed from them. And number one, replace fossil fuels with renewables. So that's what we're going to focus on today. Where are fossil fuels in buildings, and what do you do when you have a bushfire plan and a flood? Well, we've got central heating boilers that often, in fact, the vast majority will be burning gas, coal, diesel, and to a lesser extent LPG. Domestic hot water systems, which are also burning gas in its different forms. And then we're using electricity. And so even though we're really renewable here, we're incredibly lucky with our renewable energy generation. There's still 20% that's non-renewable, and that's very peaky. So if it's often associated with winter evenings. And so if you have a lot of electricity consumption in that period, you can just end up with it basically by default going to a coal or gas generation. And the sun doesn't shine at night, so you can't just replace it with solar panels. So what are the experts saying about this? And the New Zealand Green Building Council will be my go-to organisation for looking at this. And they've developed a net zero carbon roadmap for New Zealand buildings last year. Really good document. I'd really encourage you to read it and to use it as support for the decisions you're making and recommending to others. And they want to ensure zero carbon buildings are altered, or the government needs to restrict fossil fuel combustion in new buildings by 2026 and eliminate their use in new buildings by 2030 through the building code. And if we look at emission profile, it's important how we build a building, and nearly 30% is taken up by concrete and steel and transport and waste and whatever else in building the building. But then a whopping 70% is in the occupation over the next 60 years. And that's almost all, well, 70% is energy, and there's a little bit associated with water too. So again, we're going to just keep on focusing in. We're looking at that 70%. We're looking at consumption. We're looking at the material, the use of the building. So New Zealand Green Building Council recommended some standards. 2019, it feels old now, but existing buildings need to look at a carbon reduction plan with strategy to phase out combustion of all fossil fuels on site by 2025. And their suggestion is that new buildings shouldn't have fossil fuels combust on sites. So these are reasonably bold statements, but we're living in some very bold times. And so as we progress through, no fossil fuel consumption in 5 years' time, 4.5 now. And you could say this is the ravings of some minority people, and then you look at who it's funded by. So Argosy, Bayleys, Precinct, Racine, Warren and Marnie. Now, Precinct and Argosy between them control multiple billion-dollar property portfolios, and they funded this roadmap. So we're not talking about a really isolated group speaking to themselves in a language that's obscure. This is very simple and clear and sets out some very, very understandable but also achievable goals. So it really begs the question, how can we do it? Well, first of all, we need to measure. What is the demand? What is the system for? What's the function? Do we need it? Can we redesign? Can we minimize to optimize and reduce the function of the system? There's a lot of interest at the moment in passive house, and so there should be. And as it evolves, there will be hopefully less heating demand, but there will still be some, and in not all buildings can you make it completely passive. But we need to be starting off at the top of the tree. It's very much like the waste hierarchy. You don't try and recycle everything you could possibly produce. You start to try and minimize what you're producing. It's exactly the same in energy. It's just a natural process. And so if we can then, once we've measured and minimized, we then try and eliminate, and eliminate meaning fossil fuels. At the end of the day, all energy in our planet comes from the sun. It's just a case of how long it's been stored for. Fossil fuels are stored solar energy from many millions of years ago, trapping carbon that was taken out of the atmosphere, and that we probably don't want to put back into the atmosphere, because the time that the dinosaurs lived here and that fossil carbon was being stored was some pretty wild time weather-wise, and I'm not sure if we really are prepared for that kind of wildness. So what can we do to make that happen? Here's an overview. There are a number of different technologies. We're going to look very much at what's practical and available now. So solar thermal, biomass and heat pumps. So if we look at solar thermal, there are 3 main technologies out there that we should acknowledge: flat plate collectors, evacuated tube collectors, and unglazed collectors. Just to deal with unglazed first, because it's easiest, they're swimming pools only. They're very good for low temperatures and high volumes and harsh chemicals, and to extend the season, but they're not really good for much else. So we're left with some form of insulated collector that is absorbing the sun's energy, transferring it to water, and then allowing it to be used at a later time. So if we look at it for an individual house, so I'm going to do both individual homes and commercial, and just because I think we all live in houses, and we certainly spend a lot more time in them at the moment. and maybe we'll be working in them more as we go forward. So it's a really important part of the emissions mix, and it's an important part of our lifestyle. In a newly built house, the average use of energy every year is 46%, and that's according to the Wales Network, the Lines Company in the Waikato. There's a number banded around a lot. People talk about 30%. That's for all existing homes, and generally really quite inefficient heating systems, inefficient glazing, insulation, appliances. Whereas a new house, it's got higher quality glazing, higher quality insulation, often higher quality heating, and yet they've still got the same amount of hot water being used, and it's the same energy used for the hot water. So actually, as a proportion, it's growing over time. A solar thermal system will provide about 75% of the energy hot water uses. So you're therefore going to reduce total household energy and therefore carbon emissions and cost by around a third, 30% or so. And in this way, there's a really huge ongoing benefit. And I really emphasize this because I've got quite a background in assessing home and home performance. And in a low income home, if you can reduce their monthly outgoings on energy by 30%, that has a very significant impact on household budget, on affordability, on food, in kids' lunches on the table. And it's not to labour the point, but if there's anyone out there who's involved in the specification, involved in the design, involved in the requirements around affordable homes, it is important that the home is affordable, but it's also important that the home is affordable to live in. So we need to make those balances. Solar thermal can also be used in parallel with solar PV. It's not a competing technology. Unfortunately, there's quite a lot of selling going on where people really just want there's commission-based sales and people want to sell stuff. But if we're smart about how we use technology, they can sit side by side very, very well for even lower bills, energy independence, and environmental sustainability. So hot water is usually the single biggest contributor to CO2 emissions from a household on ongoing energy use, because it's all year. It's not just like a heating load where you have it for maybe 3 months, 4 months a year, depending on the location. And also, again, heating can be mitigated with efficiency measures. And so we should also try and mitigate our hot water use with efficiency measures. And so this has been represented really well by the New Zealand Green Building Council under Homestar. And in the 6 Homestar quick list, you can get 1 of 10 of the required points for compliance by installing a solar thermal system. And it also contributes more, up to 6 points if you do it with the full Homestar assessment toolkit under their EHC5 section. And really importantly, solar hot water under Homestar, and I would suggest this in all good design, is considered before other types of renewable energy generation. It's an efficiency measure. It's the same way as you insulate a house and then you look at the heating load. You wouldn't just build a shell and say, I want to heat it, so I put a heater in, and then think about insulating it. What you want to do is reduce your energy consumption, mitigate it, and then try and use renewable afterwards. So the solar thermal, by providing 3/4 of that energy use, is reducing your energy consumption. And then if you combine it with PV, if that's the track you want to take, you're getting more points, and it's much easier to get the renewable energy points under Homestar, which there's people who are familiar with that, but otherwise have a look at the Homestar information on their website. It's really good. So it doesn't have to be a great big blot on the landscape, and they combine very well. These are a number of installs that have been completed locally. So what does it cost, Hey, I'm saying all this stuff. Can we afford it? Well, it's about $4,300 for most new builds. That's your 3-bed, 2-bathroom house, which the majority of houses today are being built as. That will get you a 30-tube collector on a 300-litre cylinder. It doesn't include the cylinder. I'll go into that just below. And then about $3,500 for a smaller house, 2 or 3 people. The top one's good for up to 5 people. You need to have a cylinder, but you need to have a cylinder to store any kind of renewable energy. It doesn't matter if it comes from a solar thermal, comes from a heat pump, comes from solar PV, or burning biomass, because we're dealing here with energy in real time. We're taking the energy from the sun and we're putting it away, and we're just storing it overnight or during the day, I should say, and then for the next morning as well. So it's real time. The only reason you can have instantaneous water heating through, say, gas water heaters is because that solar energy has been stored as fossilized carbon, and then we set it on fire. Instantaneous doesn't actually happen in nature. It's really important just to have these kind of high level and broad concepts to fall back on, to explain, oh, well, why is it not quite as convenient? Oh, well, because the sun doesn't shine all night and I want to have a shower at night. So if we're in current account carbon, if we're in current energy, we need to store a little bit for a little while. And so your cylinder is going to have a cost to it associated, but that's a battery essentially. There's no electric batteries around that you could get for under $2,000 that will store a 300 litre will store 18.5 kilowatt hours of energy. The last time I looked at an 18.5 kilowatt hour battery for electricity, it was going to cost me about $30,000, and it wasn't fully rechargeable and dischargeable and disposable at end of life like a cylinder. So let's look at what is most appropriate. A battery is an amazing device to drive a car. A hot water cylinder is less so, but there's horses for courses. And then you can integrate it with central heating systems or wetback. It can be integrated with a building design. There's one up in Lake Hawea. I don't think it's too intrusive. Maybe we've got some architects that can tell me whether or not they hate it. So let's move on to multiple residential and commercial applications for solar thermal. Domestic hot water has a really variable energy use depending on the building typology. And so in some buildings, it can be the dominant. In apartments and hotels, residential care, sports facilities, food processing, excluding refrigeration, depending on what type of food processing that is. Of course, in an office building, it's not going to be the dominant use. So efficiency around lighting and appliances and HVAC will be a more important option. But in other buildings where if we break it down, how much energy goes into hot water, then it becomes more of a priority. And so in a commercial context, we're usually looking at around the 50% mark because we have seasons. We have winter, we have cloudy days. If we have too much output in summer, if we're aiming for 100% generation all year, that means we have to meet 100% in winter as well. And so in summer, we might have double the output. And so it becomes very, very difficult to square that off because you've got a huge output here, which is well beyond what we actually need because summer is much more intense for solar radiation, and we have longer days. So it's an energy saver. Really important to understand. It's not primary generation. It's to offset, it's to reduce, it's to mitigate the use of energy. And it must have a centralized hot water system with a ring main throughout the building in a commercial context. You could have scattered systems, but certainly you wouldn't have an apartment building with 15 collectors on it, 15 cylinders, and all the pipework in between. It'd be a nightmare, and it'd be very overcost. But it can also be really cost competitive and really significant for Green Star. Again, back to New Zealand Green Building Council and their ratings. And under ENE1, there's up to 10 points available. So there's some projects that I can show you, like the Summer Gardens one in Takapuna, where there's been a big value management process that's gone through and quite a lot of cool, neat stuff has dropped out. But the solar thermal remains because it's contributing significant points to their Green Star assessment. And as you can see, it's on the roof. And there's a reasonably complex roof here. We've got a number of different roof lines and services and facilities. Interestingly enough, this is a plan of the roof. It doesn't quite give you the actually, can you see? I need my my little thingy, don't I? There's my little thing. Spotlight. Here we go. Woohoo! So this is the raised up piece of roof that you saw in the previous slide. And what I'm trying to demonstrate here is that the spotlight doesn't allow me to click. There we go. So here we've got 37 apartments, about 4,500 litres of hot water a day. We're going to be using 16 solar thermal collectors on the roof. and we're forecasting about 70% reduction. That's because we're able to store a lot of hot water, and we're able to get through the evening and the following morning really well. And it's important Green Star point contribution. If we just have a look at the roof area, it's quite important to understand the practicalities of this type of system and how they work in with a building, because that's the area required for the solar thermal. I've just done it in green to make it a little bit more obvious. And then we've got a PV area for the contribution to the penthouse. Now that is just for contribution, and I think they're also maybe running some of the lights around the building on it. So you could say, well, look, maybe it's easier just to cover the whole roof and, well, to use PV for the generation of electricity to then heat water to provide it. And you know, theoretically that's simpler, but the practicality of it, because of the difference in efficiency, mean that a solar PV system would look much like this, and that's being very, very rough. It's not accounting for shading, it's not accounting for spacing. So if we're going to generate heat energy, we use a heat energy system, a thermal system. If we're going to generate electricity, we use an electrical system. And the two can sit quite happily and play nicely together and contribute themselves. And so when we've got an apartment building, especially, you've got a tall building, it's got quite a small footprint, it's got quite a lot of density and got quite high hot water use. So a thermal system makes a lot of sense. If you've got a massive, great big warehouse or a shopping center, huge roof area, not very much hot water use, lots of electricity, lots of HVAC, lots of tills and lights and bells and whistles, great, cover the roof in PV, generate electricity. But if we've got a thermal load, let's use thermal generation. So I'm just going to go through my trade secrets, so you guys will all be fully competent solar designers by the end of this session. It's always preheat for dedicated cylinders. And you must retain the heating capacity, because there will be cloud, there will be winter, there will be rain. And all of those things mean that solar thermal doesn't do as well as it could on a bright, sunny, beautiful, long summer's day. And still people want to bathe and shower and wash up and all those darned things that you do with hot water on a rainy day. So people want hot water. So you have to retain the capacity to provide it in times when there isn't enough sun. We always design the preheat cylinders depending on the hot water use profile. And so if the use is in the day, we don't really need to store that much because it's being generated and it's being used straight away, real time. But in the evening, and you know, apartments, for example, it's a good example. Most people are going to have the shower in the evening or in the following morning. The sun's not available at those times, so we use more storage. We keep it really simple. And that's important because someone's going to have to maintain this and understand it that isn't highly specialized and technical, and it's going to be there for the next 20 years. So let's make it simple. Ring mains, it's getting a bit technical, but we carefully design a ring main so that we can get additional benefit. So when there is solar energy available, we're not just losing all the heat around the ring main through electricity, the sun can actually make that up. Reliable modeling and monitoring is really important. With something as complex as solar thermal, it's important that it's defined from the outset, and then that informs project-specific design and critical. And it's, again, it needs to be from an experienced specialist. It's kind of like a motor has a pump in it often. Mechanics can understand all the motor sections, but if you ask them to take apart and remake your pump, they're going to go, nah. It's a whole different world that exhibits in that little pump. And so it's a similar thing with solar thermal. We can have hydraulic engineers understand the whole building and they understand systems, but the solar thermal's a slight beast in itself. So just to give you some examples of the spread, this is at Lake Karapiro, the canoe race in New Zealand High Performance Centre, relatively small system, and they're only using around 650 litres of hot water a day. And our girls and boys that are smashing it get into a nice hot shower afterwards, which is awesome. University of Otago Dental School, so we've got roughly twice the daily hot water consumption. and that's being backed up by electricity, so it's very, very renewable system. A Lakeview holiday park in Wanaka, a much more extreme environment and massively varying hot water demand. Now, the nice thing about tourism, when we get some again, but it's, even domestic tourism, it applies. Usually we get more, especially with a campground, you get a lot more visitors in summer, and helpfully we get a lot more sun in summer too. And so the profile of when you're generating the most heat versus when you're using the most hot water fits really nicely. So that's another, important consideration. There's the daily curve, and then there's the annual curve as well. And we want to try and choose a technology that suits. If people come with a project and say, hey guys, I absolutely smash the hot water every winter, and then we turn off for 3 months in summer, solar thermal is probably not the right technology. So live monitoring, I mentioned earlier, there's a link to a live monitoring page, but I've helpfully made it in the presentation for you guys. So it shows how much energy the system saved since the get-go, what's going on with the temperatures. This was a chilly time. And since it was installed, so I went to this yesterday, I think. And so since March 17, so a bit 3 years, we're having to keep on changing the integer. Because first of all, this was weeks of saving of energy to run a typical New Zealand home, and now we're on months, and I think we actually need to go to years, because 172 months it's kind of doesn't mean very much actually. I can't do the maths that fast in my head. That's 14 years and a third of savings of running a typical New Zealand home, with 9,000 kilowatt hours a year. So the savings are adding up. So that's solar thermal for you guys. That was fast and furious. Now we're going to look at biomass boilers. They're good for central heating. They're good for domestic hot water. They're good for process heat. It's quite a lot of info on here, so we'll just take a minute. There's central heating and domestic hot water demand. Really important to understand, these are a primary heating system, as in they'll do the full peak load. They don't require backup. Unless you're really nervous that it wouldn't work, but there's no reason to be. So unlike a solar thermal system, which is a supportive technology, it's a mitigating, it's a reducing technology, this is a full service technology, and you can combine the two for absolutely amazing outcomes by reducing your fuel consumption and with solar thermal, and then having full capacity with 100% renewable fuel. In this country, they're going to mainly burn wood. There's some other fuels in large commercial applications like miscanthus. And I even lived on a farm for a while in Wales that burnt straw bales. They used to put an entire straw bale, like a big round one, into the boiler, and occasionally set fire to the compost heap when they de-ashed it. It wasn't quite cool enough. But in New Zealand, our wood is wood pellets, wood chip, and firewood. The firewood, let's just park that. That's a domestic. Really, I'm going to focus much more on more automated systems. But in individual homes, these fuel sources are really very appropriate. They're used in schools, universities, student hostels, apartments, hotels, motels, commercial buildings, swimming pools, sports centres, anywhere that has a heating and/or domestic hot water load. They're also used a lot in process heat. And you probably would have seen the switch by Fonterra of their Waikato factory to pellets. That's really significant. And funnily enough, the biggest user of pellets, wood pellets in the world, is the UK now, because in their coal-fired power stations, they're now firing hundreds of thousands of tons of pellets instead of coal. And it would be one of the biggest success stories in the UK's decarbonisation efforts. So this is really significant stuff at every scale. So I'm going to focus in on wood pellets because it's the most flexible and the most adaptable to different situations. It's the lowest carbon fuel available in New Zealand. And it's really important to emphasize this point. If we look at the numbers, I'm going to get my magic wand out again. Here we go. All right. Da-da-da-da. So taken from the emissions database from the Ministry for Environment, quantifying your emissions, wood pellets are 0.003 kilograms of CO2 per kilowatt hour. Now, electricity in this country is really renewable. It's 80%. We're doing really well. It's, you know, what, 100 times? No, sorry, 30 times more CO2 intensive than pellets. Just the fuel origin, and then, you know, let's get into gas and diesel. They're 100 times. The reason is wood pellets in this country are made from waste materials. They're made from waste sawdust and waste wood shavings. They're not going out and cutting down trees and hogging them and turning them to pellets. They're just taking waste streams. So all of the carbon in those pellets is already accounted for in the felling of those trees, and that's then recarbonized when it's replanted, and the manufacturing. So you buy a piece of wood, or we send timber to China, there's a carbon load in there, as it were. But this is made from the waste product. So there is the only carbon intensity in there is basically from the manufacturing of the pellets and the delivery of them. So a little bit of fuel, and this is a number that may well be reducing because of the way that wood pellets are made in this country. It's already an absurdly low number. So if we just look at how it compares when we burn it and heat things, we've got condensing and standard efficiency boilers. And if we just compare that to, say, a heat pump, now a heat pump works at 300% nominal. You know, there's a range. It's a moving target, but let's just call it 300% as an average. They'll be lower and they'll be higher. So that gives us, if we're using electricity, a carbon intensity of 0.0326. It's still 10 times more carbon dioxide emissions per unit of heat than burning pellets. I'm really excited by pellets. I've been involved in environmental stuff and involved in buildings and sustainability for the last 15 years, and I've never seen numbers this good before. And it just, I think it's an incredible opportunity for an indigenous fuel. And so, yeah, if you compare it to a gas boiler, 64 times more CO2 from a gas boiler using natural gas, 73 times more from an LPG. And diesel, my God, I mean, would you park your car next to your house and plug the radiator into it? Probably not, but a lot of diesel boilers are installed in houses. But it's 100 times more CO2 than a pellet boiler. So it's difficult to understand why we're not using this more already, but that's fine. Well, that's history. We're in today, and now we can start. So presumably we're not using it because the fuel is difficult to get hold of. Well, in New Zealand, it's, as I said, 100% renewable. There's 100,000 tons or more manufactured in a year here in this country from waste materials. We're actually a net exporter of pellets. We sell them to Korea. In the past, they've gone to China, to Canada. So we're sending a renewable fuel, 100% renewable fuel, the lowest carbon emissions available overseas, and buying oil and gas and coal. So there's some interesting questions to be asked here. There is distribution across both islands in bulk and retail. So you can get it from retailers in 15 kg bags from a large store beginning with B and another large store beginning with M and with the number 10 at the end. And the bulk deliveries can be delivered by the ton. And the manufacturers are offering multi-year fuel price contracts. I'd love to have a conversation with a gas retailer, say, okay, guys, I want a 5-year fixed price gas fuel contract from you as a standard, maybe not domestic, but a small commercial operator that is going to use, you know, $3,000 worth of gas a year. They'd laugh me out the building. But it's exactly what the wood pellet people are doing, because they've got a huge mass of sawdust banked up ready. The fuel's there waiting, it just is the customer. So it must be really expensive then. That's why we're not using it. Not too bad, really. So 7 cents a kilowatt hour in bulk. Now, when I talk about bulk tonnage, I am talking about a few $1,000s worth a year. I'm not talking about Fonterra and 100,000 tons a year. That'd be the full amount that we manufacture. But we're not talking dairy factories here. We're talking about a swimming pool or an office building or a hotel or a brewery or any number of small users. Schools are a really good example. I'm doing training in a couple of weeks on schools because there's still a lot of schools burning coal, which is bizarre. And then in retail, you can buy it for 12 cents a kilowatt. So it's $10 for 15 kg bag. That nets out about 12 cents a kilowatt hour. And oh look, that's got low CO2. So the distribution is nationwide. This kind of example, again, I'll just get the old magic wand out. This is Nature's Flame in Taupo. They're national. This is Aswood in Nelson. They do the South Island. And then I can't remember the name, I'm afraid, in Invercargill and Dargaville, who are more regionalised with their distribution. And there's a lot more storage available. And we've got a doubling of output from Nature's Flame, who are by far the biggest manufacturer, last year to 85,000 tonnes a year. So this is not an industry in stagnation or in decline. So it's a safe, energy-dense, clean fuel. There's no manual handling to do. There's a truck with you can see a hose here. They suck it out of the silo, and then I think that's actually, sorry, this is the delivery. They're actually blowing it into the silo. So that we're not talking shoveling it around the place or having to deload it. There's no risk of explosion or self-combustion. You can chuck a match into them and they'll smolder away, and then it will go out. There's very limited fire safety requirements. There's an interesting project that we're involved with a retrofit into an office building in Wellington, and they've got gas boilers in the basement. They can't replace the gas boilers because it's against the building code. And being as it's a government-owned building, they really should be doing stuff to the building code. And so putting a non-explosive, entirely safe, 100% renewable fuel would make a lot of sense. There's no global warming potential around refrigerants, and we'll get to that at the end. I've got quite a bit to say about that. There's delivery methods and automatic feed from the bulk store to the boiler. So there's no manual handling either end. There's no manual handling. That's a pepper to put it into the store, and there's no manual handling to take it out of the store and put it in the boiler. And there's minimal flue gases with relatively low temperatures. They're very, very similar in emissions profile, at least in the visibility of the emissions to a gas boiler, not in terms of the carbon though. So if we have a little wee look at a cutaway of a boiler here, it's technology that's been in use since the 1990s. They're off-the-shelf products. They're very efficient, 95 to 104%. We're getting over 100% because they're condensing boilers. So if you've got a low enough returning temperature, you're able to extract the extra heat from the flue gases, and through the phase change of water and the condensation of it, you then get extra energy in exactly the same way that a gas condensing boiler works, and the same principle of phase change that a heat pump uses. So smart stuff. They're highly automated. I'm going to get my wand out, show you. So here we've got a little wee auger. Oh, actually, I'll start at the top, sorry. There's a vacuum here, and it sucks the pellets, boom, and they drop into what's called a day hopper. Fill up this. Then there's a little wee auger here, and it drags them down. There's a heat, the burn back measures in here. So basically it isolates this pellet fuel supply from the burner. There's a few different ways of doing it. This is the Ercofen version, but essentially there's no way that fire can get back here and start igniting this. It's entirely isolated. And then there's another little auger along here, along with a fan. And so the auger pushes, in the Ercofen context, the pellets up underneath, and they come out like a volcano. They come out the bottom of the grate and then burn very, very, very rapidly and hot. The fan blows air inside here, and there's another fan at the back that's taking the flue gases away. There's lots of cycling going along, lots of heat, lots of secondary combustion, and then a big heat exchanging jacket where the water is, which then goes out into the building, does its job, warms up the building, comes back in, gets hotter again. So in operation, They're very similar to a fossil fuel boiler. They're really, you know, we don't need to be freaked out by this stuff. And then it de-ashes itself. It's got a wee cleaner here that cleans off the ash from there. And then it's got another cleaner here you can see in the bottom that sucks the ash, another little auger, brings the ash out into this big can. And when you're done, you pick up the can, you put it on the garden, and you grow roses with it because it's 100% certified organic potash fertilizer. So we're not talking about sulfurous yuck that a coal boiler generates and that terrifies everybody. We're all good. So there are hundreds of thousands of them used internationally. They're really not a new technology. So there's no regular intervention. They can be remotely monitored and parameterized. I said the automatic fuel feed. So here's a big sack full of fuel. You would plug in your filler here, and then when it wants to pull out, there's an auger, sucks, drops in the boiler, sets it on fire. Job's a good one. Containerized systems, I think, are really exciting because it means that we can do systems no matter what the building is. Take a couple of car parks up, put a bike park maybe on the side of it to really, you know, illustrate the sustainability credentials of this whole project. It's a containerized system with a plant room. It's got the pellet boiler in it. This is a small example with a single boiler and a single feed, but you can have large ones as well. Fuel store, automatic fuel supply, water and power connections, everything you need. And so you've got a really high level of cost control through doing this and consistency of design and delivery, guarantee workmanship, because it is a specialist product. We want to make sure we get it all right, and it's completely modular and expandable. So there's no real reason, if a building has got a little bit of space outside and we can plug a couple of pipes and a piece of power into it, that we can't make these conversions happen. We're lucky in New Zealand, most of our buildings and urban areas are relatively low density. Yeah, of course, you're not going to get this container right in the middle of an urban area, but then we might have a basement room instead that we can use. But in anywhere that's got a little bit of space around it, that's fine. And then you can use the container to educate and to market. This is some other random artistic container that's not necessarily anything to do with pellets, but it's pretty. And I think it's a really good opportunity for people to put their credentials and the actual action that they're making front and center and demonstrate this. It doesn't need to be our guilty little gas boiler secret that's hidden away in the basement. This is something that's really important for us to talk about and to get a lot of additional value from in that process as well. So it also applies domestically. This is an example of a domestic system. It just looks like a little filing cabinet in your garage or wherever it might be. There's a hopper on the left, which contains the pellets, and the boiler on the right. They're available with a weekly refuel and a monthly de-ash. It's not a big deal. Or you can have them automated as well. Running costs are very comparable to diesel in the retail bag. So that's not even buying bulk tonnage lots. That's going down to Bunnings and getting 15 kilos at $10. They're really high efficiency. They come under the ULEB regulations from ECAN, so you can install them anywhere in the country in any airshed, and they're going to have a positive effect in terms of providing heating without the emissions. And again, there's no global warming potential refrigerant. So whistle-stop tour of pellet boilers, that was. All right, now heat pumps. I'm not going to spend a huge amount of time on heat pumps, which is good because we don't have a huge amount of time. But in commercial and buildings and homes, they can provide heating and domestic hot water. There's a lot of product offerings and there's a lot of efficiency. It's really important to look at full system design, maximize efficiency, get the best outcome, and use technology appropriately. I'd highly recommend you go to the low carbon process heat replacement and commercial building application recording by the guys from Lumen. It's not really about process heat at all. It's about heat pump heating in buildings and kind of dwells on some other stuff. But I'm not going to go into massive details about heat pumps because they already have. But fundamentally, what I want to just explore a bit is about refrigerants, because they're at the heart of how all heat pumps work. So you have phase change, the change of state at different pressures and temperatures, and that is what gives us the multiplier effect. But refrigerants have something called global warming potential. We need to be considering this. It's something that is not necessarily on everyone's radar. It's why I want to raise it today. What is it? It's a multiplier of how much more potent any gas is for causing global warming. So we often talk about methane in the New Zealand context. It's 25 to 36 times more intense than CO2, and so therefore it has to have different mitigation measures, but it's shorter lived and yada yada. There's a lot of discussion around that. Exactly the same with refrigerants. They have a global warming potential number. And so the lower that number is, the less environmental impact there is, the less climate change, the less we're going to alter the amount of heat that's retained in our atmosphere during its manufacture, its in-service and end-of-life disposal, if it's released. Now, a lot of refrigerant is released, unfortunately, because things break down and the refrigerant goes off, or it's not disposed of correctly at the end of its life. And you see it in a skip, you just know that the refrigerant line's busted, the gas disappears, it's completely non-toxic, it's completely invisible, it's got no smell. You don't know it's gone, but it's doing a lot in the atmosphere. And so the global warming potential of refrigerants is a 21st century version of ozone depletion. So we've had CFCs banned because of the bloody great big hole in the ozone layer that's right above this country. And we all know with the melanoma what that means. So we have an understanding here of what long-term consequences there can be from short-term decisions. And so now, in the position of climate crisis, we must consider the refrigerant's global warming potential. Unfortunately, the most common refrigerants used in the process of heating and hot water heating in New Zealand and often around the world have very high global warming potentials, 2,000 times the CO2, which is the baseline, 1,300 times the baseline. So what does this mean? Or what alternatives, no, sorry, what does it mean? If you had a small domestic heat pump and it leaks refrigerant at the end of its life, okay? It might have a kilo of refrigerant in it, or it leaks sometime during its manufacture, during its use. It might have 1 kilo of R410A. So it's 2,000 times more potent than carbon dioxide, which is the base case. So it's the equivalent of emitting 2,000 kilos, i.e. 2 tons, of CO2 in terms of how much impact it has in the climate as a global warming gas in trapping heat in our environment. In the New Zealand context, that's the equivalent of 21,000 kilowatt hours of electricity generation in CO2 emissions, because we've got really renewable electricity. So it's actually an enormous amount of electricity, or 5.5 years nearly of a family of four's hot water use, using 200 litres of hot water a day. That's a reasonable amount of hot water, that's a very comfortable living style. So it may well be longer for less hot water use or smaller families. So fundamentally, if you have a heat pump which has got a standard refrigerant in it, and something goes wrong and that refrigerant is emitted to the atmosphere, you've already in debt, let's say, carbon debt. You've emitted the equivalent of 5.5 years of family hot water. This is just 1 kilo. Large commercial systems will have multiple kilos of it. Hopefully they're less likely to leak and they're going to be dealt with much more professionally at the end of life. But it is a fact that we need to consider. I was having a really good chat with Sam Archer from the Green Building Council earlier, and he said that it's something that is being looked at globally, and it's something that we're really needing to focus on here as well. Doesn't mean we shouldn't use heat pumps. What it means is we should be, I've got to turn the magic wand off. We should be looking at alternatives. So there are lower ones. R744, just coin numbers, which is also known as carbon dioxide. It's the base case. So it has a global warming potential of 1. R1234ZE, which is my favorite name, is a global warming potential of 7. So those are both direct replacements with appropriate systems, of course, for 134A, which, if we just go back a slide, had 1,300 times the impact. So we're now talking about 1 and 7, much nicer numbers. And then R32, which is got a direct replacement for 410, which is 2,088. Now we're at 675. It's not too bad, better. So if you're going to specify, ask questions, get a better form of refrigerant. And if they say, roll their eyes at you, oh, it's not possible, walk away, because there's plenty of manufacturers and suppliers and installers out there that do good ones. So what opportunities there are? I think we really need to concentrate on replacing low efficiency fossil fuel burning appliances. So instantaneous gas water heaters, they're a bit of a nightmare, in all honesty. They burn a fossil fuel, it's 100% non-renewable, and they burn it at 80% efficiency. That's their badged efficiency. So regardless of how much it drops off over time or whether or not that changes. So why do we use them? That's a really good question. We fundamentally need to question how we design and specify things. Do we have a place in our society for instantaneous gas water heaters today? Large inefficient boilers, especially unnecessarily centralized systems. So the Temper Zone have done some really fantastic work on this in New Zealand, up in the far north, where they had a massive coal boiler in the middle of a hospital. And so instead of doing that, they put heat pumps around the campus. And so each heat pump had a function of a smaller area, because you can't really do the same volume with a heat pump as you can with a coal boiler, but you decentralize it and you replace the inefficiencies. You need to specify the lowest global warming potential refrigerant. We've just been through that. Maintain and very carefully dispose of the systems at end of life, because just one little crack pipe, a little bit of gas, you don't even see it, can't smell it, nothing happens. It actually does. There's quite significant things happening, just they're invisible to our eyes. They're much better for lower temperature applications. So we want to be on the highest point in the heating curve. We don't want to be trying to push them to the limits. And they're good in buildings that require cooling as well as heating, but we've got to do the efficiency first. You know, there shouldn't be masses and masses of heat and cool going into a building. It should be a more efficient place first. And in a building that is completely impractical to use bioenergy or passive heating and cooling design, well, then a heat pump is usually a good option. So, you know, more density, urban areas, etc. So quick case study. I've ranted and railed against instantaneous gas water heaters, and you're saying, well, you know, they're really practical. Well, heat pumps can be pretty practical too. So here's a commercial system example. There's a passive house certified apartment building in Auckland that's to be built. It's going to have multiple carbon dioxide powered heat pumps with a COP of 4.7, so that's 470% efficiency, not 80%. And it won't be burning fossil fuels, and it won't be losing low efficiency electric hot water cylinders. It's a pretty dense living environment. As you can see, there's 4 apartments, single beds on each floor. And then on the ground floor, we're going to have some heat pumps here in this void. They'll be stacked up the building. I'd like to lift my mouse and it's not coming up the building, but you can imagine vertical height. And then a series of cylinders, which will be hidden behind the bike racks. And then a ring main circulation system. We've worked out that the running costs were something absurd for all 22 apartments, something like $40 a month to do hot water for every apartment, like total. And that's me, done. Questions? Any questions?
Well, thanks, Marcus. That was quite fascinating. And it does just goes to show how many alternatives there are out there. Now, the sign of a good presentation, of course, is the number of questions that come in.
Awesome.
So I can inform you we've got plenty of questions. We have questions from at least, and I'm mentioning the names just to let people know that I have seen they've got questions from Gohar, Russell, Barry, and Alexis, and probably a couple more coming in now as we speak. I'm going to open up the microphones in the order that I saw them, okay? Which I think is the order that they were raised. So I'll just open up Gohar's microphone. When you do get to ask your question, can you please just say who you are and where you're from? Because we've got a lot of people online and they're interested, I'm sure, to hear some context around where you're from as well. So Gohar, your microphone is now open.
Good afternoon. This is Gohar from University of Auckland. Thanks for your nice presentation. So at the beginning of your presentation, you were talking about solar water heating. Yep. Just wanted to know if you have any idea about the payback time of these solar water heaters, maybe per meter square, if you can report, I would appreciate it.
Yeah, so quite a few variables. It depends on domestic or commercial, really fundamentally because of how much is the electricity or the fuel that we're offsetting going to cost. Because the higher the cost of your energy that you're offsetting. Can we just mute that microphone, Mike, while I'm talking? Sorry,
yeah, I've taken the microphone off. I'll open up again in a second, Gohar, in case you have something to come back on, but
Thank
you're
you.
off for a second.
So the cost of the energy that you're displacing is really fundamental to the payback period, because if you're on a contract where you're buying vast amounts of electricity as a university and you're able to negotiate down to maybe 12 cents or 15 cents a kilowatt hour, it's going to have a significant impact on payback compared to, say, a domestic customer who are nowadays, according to the MB figures, averaging 29 cents a kilowatt hour in a domestic setting, where we actually use a conservative number of 25 cents a kilowatt hour for the payback calculations. We would average 5 to 6 years. I think that's been reasonably conservative, because people have come back to me and said we're all kind of squared off by 4 years. But I'd rather overpromise, underpromise, and overdeliver. That's it. So in a commercial, it very much depends. It also depends, I guess, what sweet spot we want to hit. So I said that there was a range of 40 to really up to 70% of reduction in energy consumption. As you get higher up that range, the net benefit, the marginal cost is greater. So the net benefit is lower, the marginal cost is higher. So you end up with a diminishing return. So it's the usual 80-20 rule, I guess. So if we're aiming for 40 to 50% of offset, then you would see a payback usually in the 8 to 10 year bracket, depending on cost of energy. And it really does depend very much on cost of energy. And I'd encourage you not just to look at just a simple payback, but also the net present value, because that system's going to be there for 20 years, and the value of the capital now is greater. Mike can explain that far better than I can probably one day, but your capital appreciates more over time. And the other thing is that looking at the carbon emissions, if you're offsetting electricity, there's probably not such a great argument for the carbon side of it. But if you're going to offset gas, which is often the fuel of choice for water heating, then it's a huge carbon benefit.
Thanks for the plug, Marcus. Business Case Workshop, 1st and 2nd of July. I have opened you up again, Gohar, in case there's any comments on that.
Yes, thank you for the first question, but if I can ask another question. So my question is that is the system, this solar water heating, is it portable? Because like commercial building owners usually lease the building, as far as I know. So like, is it, so usually they lease it for 10 years. And then if the payback time is 8 to 10 years, it's not worth buying that. Is it something portable that they can move it to the new building, or it's fixed?
I mean, it's all fixed, because otherwise it would blow off the roof. But in theory, it's portable, but reality, you almost certainly wouldn't do that, because the cost involved in redoing it all would just negate the savings. And just the practicalities of trying to move this thing around would be a nightmare. I'd suggest that you instead discuss it with the building owner in terms of the overall benefit that it's going to provide to them, and therefore the attractiveness and tenancy. So we've seen a lot of upswing through the New Zealand Green Building Council work here and also in Australia, that when buildings have efficiency and environmental improvements, they become more valuable on a per square metre tenanted basis. So it's something to discuss with the building owner.
Yeah, thank you so much.
No worries.
Thanks, Gohar. Next on my little list here is Russell. So you are now open, Russell. If you'd like to introduce yourself, please.
Hello, I'm Russell Bailey. I'm the Energy Manager at the University of Auckland, and I've got a couple of questions in the stack. I'll do one and then we'll let somebody else, and then I'll come back with my second question later on.
Cool, thanks, Russell.
It's to do with the seasonality of the electricity load profile across the whole of the New Zealand system. So if you've got a solar hot water system and you've got 3 weeks of rain and cloud in the middle of winter, and you've got an electric element in your cylinder as your backup, then you're consuming electricity during the worst time for the New Zealand seasonal electricity generation cycle. It's when the transmission in the network is most loaded. It's when the the lakes are at their lowest, so we've got the biggest carbon burn going on. Fortunately, you also talked about domestic hot water heat pumps. If you had PV panels driving domestic hot water heat pumps, then during that same 3 weeks of wet and cloudy stuff in the middle of winter, you would only be drawing 1/3 of the electricity off the grid as you would be with the electric backed up solar hot water, which would be reducing the peak loads, which would be reducing the infrastructure constraints of the number of peak power stations, the transmission cables and the local networks. What commentary have you got on that?
Yeah, no, it's a really good point. So I'd unpack it on a few different layers. If we just work from the end back, so you said heat pump with PV, but then cloudy and rainy weather. We can assume that the PV will be generating nothing, so we will just be using grid electricity. But like you said, it would be on a multiplier effect of the heat pump, so that's a benefit. I think it's a really important question. It becomes, well, actually, sorry, I just carry on with stepping backwards. So if we had solar thermal and it's not contributing very much at all to the total energy, and you have to make that up with electricity, in an ideal, like you're kind of talking New Zealand Inc. here rather than individually chosen situation. But in an ideal scenario, you'd actually use a night rate heater in your hot water system to back up the solar. And so if you do it after, say, 10 p.m., you're shedding most of the load available or that's on the grid for the peaking that you talk about, and you should be able to do it mainly off run of river and the wind turbine generation. There will be some peaking, I'd imagine, but it'd be much less. And you struck a point that's really difficult to square with individuals, because everybody wants to have their own system set out in the way that works for them. But what you're talking about is more of a network-wide issue, and so it needs to be incentivized and maybe even legislated around by government, and individual choice becomes quite difficult. And if you allow everyone individual choice, it might not be the best outcome for the entire country. So I think it's a really good point. It would be interesting to look at the proportion difference that makes, and whether it's really significant. I know the Parliamentary Commission for the Environment did a study a few years ago. It had solar thermal probably at a lower output than I would say it could do, but her conclusion was night rate electricity was a very good and wide-reaching solution for this in general. And it's actually an incredibly cheap and easy way of doing water heating, but it relies on individual behaviour and probably a little bit of legislation as well.
Okay, Russell?
Yep, that was great. I'll just add a bit of supplementary in there for you.
Yeah.
Mum and Dad installed a domestic solar hot water system in 1980 when they built new, and it went for a whole 25 years before their first little bit of maintenance, and that was a new circulating pump for $150.
Awesome.
And then it kept on going for another decade or so until they sold the house. So if anybody's worried about maintenance, the trick is to get the right plumber to install it properly.
Yeah, exactly. That's awesome. Great.
Thanks, Russell. We'll come back to you with your other question. What I'd like to do now, though, is move on to Barry. Barry, if you could introduce yourself, please. I've just opened your microphone.
Thank you. Marcus, thank you very much for your presentation. I really enjoyed it. My name's Barry Reid. I work for the Ministry of Education. I'm a property advisor for schools.
Okay.
So I found the discussion around boilers particularly helpful. because we have a lot of coal-fired boilers around the country.
Yep.
And my focus is the Bay of Plenty, where we're kind of phasing them out, but there doesn't appear to be a lot of knowledge around the alternatives. So I'm quite interested in talking to you further, particularly when you mentioned about the training that's coming up. I'd like to know a bit more about that, please.
Yeah.
But I was really pleased to hear that that resource is available and being well used, and that being in right beside the central North Island forests, that we've got a great opportunity to use a renewable resource with such great qualities, but we're not really taking full advantage of it at this present time. So that was really what it was about, just sort of truly appreciating the number of applications, whether it's solely in schools, but also other applications domestically as well, and the benefits that we can get, but particularly for schools, and just being able to convey that message to boards of trustees and principals that heat pumps aren't the end all and the be all to solve their problems.
Agreed. Yeah. So there's a few layers to this. On the 5th of June, I'm running another webinar specifically focused on pellet boiler solutions for schools, and so that's for the Bioenergy Association. If you go to bioenergy.org.nz, on their front page, in fact, they've got an events list, and that's been designed for exactly what you're talking about, and we've tried to send it out to as many principals as we can. And a challenge, I think, really in this area is that it's very fragmented. And we've even tried approaching the Ministry for Education directly, right up to quite a senior level, and saying, look, we think there's a huge opportunity to do this in a considered way, in a strategic way, rather than it going school by school, which seems to be the preferred methodology for procurement. That we actually say, look, we can do some really for the containerized systems that I showed you. Sorry, my screen's gone all crazy. So we can do systems. I'm just coming back to that slide where it's entirely self-contained, and so it's really a kind of plug and play, drop-in replacement for a fossil fuel boiler. And I think that's an ideal scenario in a school, where you plonk a couple of containers down. And even further to that, it's really interesting what you're saying about you're in the Bay of Plenty. So am I, and I think there's an incredible educational story here, and emotional connection. We've got a generation of students who are feeling a lot of stress about climate change, and the strikes and the protests are a really good example of what they're feeling, a demonstration of it, and for bloody good reason, frankly. And so if we can demonstrate actively and positively what measures the schools are taking to mitigate that, and if we look at a school's impact, the actual direct impact of the school, if we exclude, say, the transport of the pupils to school, by far the biggest impact is the heating system, because you're often burning a fossil fuel. And so if we can remove that fossil fuel and demonstrate it, and we've developed classroom materials to do that with the kids, and encouraging others in the industry to do exactly the same, to approach it as a holistic process, and to replace these items that it's really readily available to do. We've got one coming up, so at Netherton School, it came out through the contestable sustainability funds that was available earlier this year, and there's a second round later this year. And we'd love just to see so many more schools in taking that opportunity, because it really feels like it's here and now, that it can happen.
Yeah, I think it would be, I think there's huge potential, and being able to maybe even team up with yourself and talk to the right people, I think we could probably set something up. I think it's a
What was your surname, Brian?
case of
Pardon?
Barry. It's Barry Reid,
Barry.
R-E-I-D.
Okay, awesome.
Yeah.
I'll look you up. And they're also on my, you can always, my details are at the end of this. I'll just bring up my details are on here.
It's, you know, a lot of it's about making use of the available space, and when you give up a coal-fired boiler and the space surrounding it, you're gaining a lot in the sense that you don't have to put something as big back as a replacement, and then you, well, maybe not, but you've also got a lot cleaner system. So,
yeah. I mean, I find it incredible that we're still burning coal. The environmental thing is one side of it, but also I go into a plant room, and I went to the Netherton one, and the pipes, the big fat steel pipes, are literally rotten from the sulfurous emissions from the coal. And you're like, hang on, my kids are breathing this? And there might be someone working in the school 30 years, and every winter they'll be breathing it. And a lot of our schools are in a little dip or something like that, in a little inversion layer, so that the fumes all kind of hang out there. Yeah, enough said, eh? Hey, I'm just going to turn the light on.
Probably. So I think it's time to move on. Anything else you want to follow up with there, Barry, or shall we move on to the next question?
Well, and we'll take from there. Really enjoyed it. Thanks.
Wonderful.
Okay, thanks, Barry. Next questioner then is Alexis. I'm just opening up your microphone, Alexis. If you'd like to let us know who you are, please.
Thanks for your presentation, Marcus. Really enjoyed it. I'm Alexis from Opera Associates. We're a client-side project manager based nationally, and we work with Ministry of Education and a lot of other government entities.
Yeah.
Now, you mentioned containerised pellet boilers, and I just wondered if you could expand on the usage and supply and demand in New Zealand currently on that.
Yeah, absolutely. Hey, this doesn't even need to be restricted to this presentation, does it, Mike? Can I be naughty and show other things? Like, not.
Yeah, if we can bear in mind, we've still got another 4 questions or so.
All right.
To come to.
Maybe let me.
We don't have a technical limit, but it's more a case of getting through some of them.
I need to find my presentation again. Let me address that with you, Alexis. But fundamentally, you've got a shipping container, which are readily available. You've got boilers. We are one of 6, I would say, distributors of good quality. I think it's all European, from my understanding. I don't think there's any other American or Canadian brands here. But yeah, a number of different distributors of boilers. And then essentially you're plugging the pieces together. And the benefit of a containerized system is that the manufacturing can be done off-site by specialists. So instead of, the mechanical services contractors around the country are all really skilled in the things that they're experienced with, but they may not have that much experience with bioenergy. And so the containerized system is really designed so that all of the kind of specialist bits are done off-site for a guaranteed fabrication, and then freighted to site, placed. They'll come pre-commissioned, but of course, for example, our company and I'm sure others would also then come to site and commission it, but then work in collaboration with the local mechanical services contractor, and in the schools context, and I guess also to a certain extent a commercial buildings context, the on-site maintenance people, and explain how the fundamentals work, what minor maintenance there is. So in terms of maintenance, I'll just get my magic wand. Here's a box in our version which contains the ash, and there's a little wee handle on it, and literally every 4 tons, so that's 20,000 kilowatt hours, so 20 megawatt hours of heating, which is a fair chunk. In most schools that's going to be a good couple of months of heating. you pick this up and empty it on the rose bed, or this is called garden bed, and you put it back, and that's all. That's all that the property maintenance manager needs to do. And then there'd be an annual service. So does that help answer your question?
I sort of wanted to know how many current containerized pellet boilers there were in New Zealand.
Oh yeah, okay.
Like examples specifically.
There's a couple at Rangipo Prison. There are some more down south. I'm not 100% sure their location. That probably would, yeah. There's, I don't know. There'd be maybe a dozen scattered around the country, because historically it's been seen as more of a plant room exercise, and I just don't know if mechanical services trades are really that creative sometimes, and it's taken some other people to shake it up a little bit and say, hey, look, there could be some really creative ways of doing exactly the same as what you're doing now, but instead of going through all of the pain of building or modifying a plant room, we can just bring a plant room here. They're a very, very well-used system in Europe and in other comparable economies, so like Argentina and Chile. In Argentina especially, they've got them stacked all over the place. So your countries where you've got quite a similar heating profile to here, it's not intensely cold in winter, and yeah, maybe a bit more space and a little bit more dynamism about how we do things. Does that help though? In Europe, the containerized ones that we've seen mainly, and you can see from that example, actually, they're encased in concrete, and rather than using a shipping container.
I guess it would be important to also consider, yeah, what material these containers are made out of, and how that offsets against the emissions you're saving. But in some cases, I guess you don't have a choice of the space restrictions or. Yeah,
well, shipping containers seems to be the most appropriate, because they're relatively low cost, they're pre-engineered, they're easy to get hold of, they already exist, and at end of life they're fully recyclable because they're just made of steel. So yeah, that seems to be the obvious solution, and then to decorate them in some way to blend them in if you want.
Thank you.
No problem. Thanks, Alexis.
Okay. Thanks, Alexis. The next question on our list then is coming from Jack. So your microphone is now unmuted. Jack, if you'd like to introduce yourself, please.
Hi, Marcus. Thanks again for the presentation. Jack here from Energy NZ. I'm just curious to know if you've ever seen solar thermal deployed with large energy users, perhaps like industrial sites. So these could be sites that might use a large amount of hot water kind of continuously. Is there a cost-effective deployment of solar thermal at sites like this, or does it kind of more depend on smaller users that can shift?
No, absolutely. I took out a slide of my presentation because I didn't want to overcomplicate things, but let me just open it up now. So yes, at scale, we're in a slightly unusual position, I think, in this country where it's maybe not as climate impactful because we've got such good renewable energy generation. Can you see that? Can you see the other presentation? Yeah, so that's 100 30 tube collectors on a roof in Mauritius, which is stage 1 of a 3-stage project. And that's delivering peak or continuous, but well, yeah, let's call it peaking output of 400 kilowatts. 200 kilowatts. And the eventual aim is to have another 3 banks of a similar size. The output over the year, I think, is 40 megawatt hours, and that's directly offsetting a diesel or a heavy oil burner. It's in a fuel, a fabric dyeing plant, and they run 24 hours. So what becomes really crucial when we're looking at this is how often they're running, because what we don't want to be doing is storing energy if we can help it. We just want to chuck it straight into the process. And so as long as they're running all the time, and we can basically, this has just got a heat exchanger in line on the boiler return. So as the water comes back from their process, it gets picked up by, say, 15 degrees or 20 degrees by that collector at a set volume flow rate, and then return to the boiler. And so you get really highly, efficient use of technology. We've done a few calculations in New Zealand for various different places, and it is reasonably challenging in this country because a lot of our heavier industry is based in some of the worst solar regions, far down south. We looked at Edendale with Fonterra, and the other thing is that they've got such a huge amount of embedded money in the infrastructure that unless we can say, I can take out boiler number 3, then it becomes a very difficult proposition. Whereas, as I said before, it's just about reducing energy consumption. It's definitely practical, and it would be around the reduction of fossil fuels. I wouldn't see it as much point if you're going to reduce electricity consumption. But yeah, it's the short answer, and it depends is another answer.
Well, that's great. Thank you very much.
No worries.
Thanks, Jack. Next question from Yachul. Just opening your microphone there. If you'd like to introduce yourself, please.
Yeah, good day there, team. You're Carl Upson, design engineer based in Nelson, associated with the transition engineering community as well as the Nelson Tasman Climate Forum. I just wanted to make damn sure I said, Marcus, what a fantastic presentation. I really appreciated the whole of it and your approach here. Also to Barry and the subsequent discussion you had regarding schools, fantastic and really interesting. I know I found the boiler section particularly good as well. Regards bio feedstock. I wondered, there wasn't much coverage of capital investment and ongoing costs between diesel-fired, say, and the pellets. I wondered if you could give just a very quick high level on that. I know there's one local brewery here in Nelson who's undergoing a process of plant upgrade and considering their boiler options. I don't think they've been particularly innovative, but I wonder sort of what could be posed to them in terms of wood chip.
Okay. So there's a few different things to unpack there. So source of heat is quite important to think about, and essentially as the heat load increases, it may, and this is a very big may, be more economic to use chip instead of pellets. But that depends very much on the local availability of the chip and basically how far it's got to be moved, because it's big and bulky and you get about a third less energy volumetrically as compared to pellets, and the quality of that supply. So now in Nelson, you're blessed with a distributor called Aswood, who do both chip and pellet, and they would be best placed to give ideas on cost of fuel. But it seems to be a bit more that as the usage increases, it goes a bit more to chip than to pellet. That can also be about the technology. You can have bigger individual boilers for chip than for pellets, but here we're talking multi-megawatt. I'm not talking small, smaller 1 to 2 megawatt scale, but in the very large sections. And the kind of efficiency, as it were, of the pellets, it tends to be a little bit less, not compared to chip. It will always be more than chip, but as opposed to, say, the commercial packaged ones that we use in Cascades. So the boiler that I showed in the illustration here, when I get to it, that one will do. that's a 64 kilowatt boiler, and we just use them in multiples, in cascades, and you can go up to 1-2 megawatts with them, but it would just be lots of small boilers, and so you can moderate it. As we get to really big users, then you'd probably have custom made large boilers, and the prices will, they're difficult to say where it's at. From our perspective, it's certainly in a containerized system where we've, say, maybe got a bit more control over all of the cost, and we know a bit more about where we're coming from. We've estimated around $1,000 a kilowatt is a good guide price, but that probably would be excessive once you start getting up to the big ones, because you have some economies of scale there. But then you also have big custom made boilers with engineering involved, and you engineers, you're expensive, man. But yeah, for the containerized systems, I'm really comfortable with $1,000 a kilowatt, up to say 1.5 megawatts, 2 megawatts.
Thanks a lot, Marcus. I appreciate the caveats you mentioned there, but that's a good first look in. Thanks a lot again.
No worries. Thanks for coming.
Thank you. Next on our list then is Yariv. Now, I think you might know Yariv, and I think Yariv might know you. Yeah. But Yariv, your microphone is now open if you'd like to raise your question, please.
Hey, Marcus and Mike. Thanks very much for an excellent presentation. I really enjoyed that, and I have actually learned a few things. Now, because it's starting to get a bit late, I'll be very quick. And I wanted to support you in relation to the question of of large-scale solar thermal, and say that the example of Mauritius is, in my view, almost sort of like a median size, like mega commercial system. We have seen, like, I'm talking about 800 to a megawatt installations of solar thermal on hotels and resorts and locations like that have an immense demand for hot water system, for hot water consumption. And the usage of solar thermal was certainly the best cost benefit value, even if sometimes it is being coupled as a preheater, and that's again the key for heat pumps to maintain storage heat. So that putting aside, I also had a very quick question about how biomass systems that are installed in commercial buildings can contribute to heat transfer. But I think that's a very big discussion. So I just wanted to sort of plant that seed and maybe develop a conversation on it. More importantly, the question.
Heat transfer, sorry, Yov?
Heat transfer systems. So take latent heat that is available from the boiler and maybe exchange it with hot air that comes in to the with cold air that comes into the building.
Okay, so a fan coil system essentially, or heat exchanging. Yeah. Well, I mean, it's a source of heat as any source of heat would be. So you would run pipework or thin coil units, and then the air would go across it, for heat exchange in passing to refresh the air.
Yeah, and I think those type of systems, especially the pellet systems, will provide fairly uniform heat and fairly constant, depending the demand, of course. But that would sort of, I guess my question is, how much energy could we absorb and quantified by, I don't know, kilowatt hours per square meter or watts per meter and so on. As I said, there's a big discussion about heat transfer, and probably we should have it over a coffee or something like that. The other question that I wanted to ask, and that's very important for me to get an answer on, is how would pellet fuel is being considered as a part of the carbon zero framework or the roadmap that was outlined by the New Zealand Cabinet Council. One critical point is to encourage buildings to move away from fossil fuels. And a part of it is that they will have 5 years to get rid of all their boilers and so on. And in my mind is, if you have already made an investment of X amount of dollars in a large boiler, could those be converted to be used as pellet boilers? And then help those buildings that are targeting net zero to reduce their capital investment? And how do you feel that would be accepted, because there's this whole topic of fossil fuels, and I've noticed that you've excluded pellets from fossil fuels?
Well, they're not a fossil fuel. That's why. No, I mean, it's real-time carbon. It's current carbon. So
right.
Yeah, it's straight from. It's not being stored. So it's it's taking biomass out of the ecosystem. But then, because in this country it's all made from a waste product, the only other place that sawdust is currently going is to landfill or incineration. So incineration is basically the same as the pellet boilers, but you don't get the net benefit. Sawmills, I guess you get some benefit, because essentially sawmills use it to dry their lumber. But the vast majority of wood waste in this country, you could say, 95% of the wood waste in this country is going to landfill. And my wife works on the landfill projects with the Ministry of Environment, and she said that there's not a great carbon impact from that, but the loss of its potential as a fuel feedstock is the carbon loss, because if we're able to offset coal from wood pellets, then we've just offset an absolute fossil fuel, or even gas. And then the other point about burning pellets in boilers, yes, it can be done in coal boilers, but one word of caution, especially when we're developing or evolving it and creating more opportunities, is that it's a coal boiler is designed to burn coal, and pellets do behave a bit differently. So it has to be done sensitively and carefully. And what we don't want is people to have really negative experiences, say, oh, these pellets are a heap of poo and we're not going to use them anymore. I'm going to just go back to coal or use something easy like gas. So there are some caveats. A modern high efficiency automated pellet boiler is a very different beast from a coal boiler that is now burning pellets. So it's just something to bear in mind. But there have been a lot of successful transformations, especially with those big building users. So I'm thinking in Dunedin and in Christchurch, and the Fonterra boiler in I can't remember, Tiawamutu or somewhere, that's going to be burning pellets. They're all coal boilers that are now burning pellets.
Right. Right. Well, that's good to know that you can actually make a conversion. I understand that the efficiencies will not be there. The question comes more in the context of an existing infrastructure in a building that has committed itself on a path to net zero, and they need to, as part of their commitments, they need to get rid of any fossil fuel or any fire in their building. Yeah, but they already have the infrastructure, so it's a cost management thing, and might be accepted. Yeah, that's really great.
Cool. Thanks, Yari.
Thanks. No worries.
Thanks, Yari. We're now going back to Russell. So you're open again, Russell.
Can I just jump in for a sec,
Okay.
Russell? Yariv did a really good presentation last week on PV as well, so I'd really encourage people to look at that. It's the main reason that PV is not really included much in here is because it's been covered elsewhere. So, Russell.
And if I can just add into that, sorry, Russell, those are available on our go-to channel, so you can get to those through the CEP website. Sorry, Russell, over to you.
Okay, I'm actually going to change my question from the one I've got posted up there, but before I do, I just wanted to join the line between Alexia, Barry and Marcus with the question of how many are out there now and how much do they cost insofar as the palletized containers, other containerized pallet boilers, and it comes back to Barry and it comes back to the individual school of trustees. I used to be on a school board of trustees, and it's this individual siloization of decision making, which is one of the things which is holding things back. So if Barry can aggregate it up to a regional ministry level, it's then the opportunity to place an order for 30 container boilers, which then enables the mass production, and the standardization, which significantly drops the cost of them. And so it's one of those
operating benefits as well. So rather than every school having to remake the wheel in terms of what they're specifying and what they're operating, you can have it centralized, because I think there's a lot of that where it's just everyone's trying to do it for themselves, but actually
so without doing Alexia out of a job, with an individual board of trustees employing them as a client facing project manager, it's the sometimes when we try and change the way we're doing things, we need to do a bulk order at the top of the system and push it down through the system. Setting that aside, CO2 heat pumps.
Yes.
How sensitive, and so instead of domestic hot water CO2 heat pumps where you're bringing in 15-degree water and single path and spinning there at 65, if we've got some small gas-fired boilers about the place in the 50 to 100 kilowatt range, and they're currently used for heating hot water systems where we've got a 20 degree C delta T at peak operating, how sensitive are the CO2 heat pumps to the inlet water temperature, i.e. returning water at 40 degrees and sending it back to the field at 60, or can you look at just the straight out lift of the temperature, or is the lift significantly impacted by the inlet temperature?
Yeah, so CO2 heat pumps perform best when you've got a big delta T. So you would get loss of efficiency, and at some point it will just get sad and not do its job, essentially. So as you get closer and closer to the cutoff point, the COP does decline, and then there'll be a point where it will just kind of spin its wheels and won't do very much at all. There's a relatively easy ways of getting around it, though, by just ensuring that you always have, I mean, this is in terms of if water's being drawn off, it's one of the reasons that we can't easily use carbon dioxide powered heat pumps for central heating, because of course the returning water needs to be at a temperature that's still maintaining some comfort out in the building. People get really grumpy if the last radiator was only at 15 degrees. But for domestic hot water, where you're drawing water through the system and it's leaving and new water is coming in to replace that, as long as we retain a buffer of colder water at the bottom and manage our calculations based on the total volume that's going to be delivered, and then essentially plus its cold water buffer, we can benefit from the stratification of heat in the cylinder and use the coldest water of incoming to go to the heat pump to get our full delta T, to get our efficiency, and then the high temperature water returns. But we do need to quite carefully manage that buffering system.
Right, so if we're wanting to replace a space heating hot water small boiler with a heat pump, then we've got to go to a different refrigerant gas with a higher global warming potential. And any recommendation of what's the most appropriate refrigerant gas-based heat pump for that?
No, not off the top of my head. I mean, R32 is the one that's being used a lot in underfloor heating heat pumps as a refrigerant replacement. But that's still 675 times more than CO2. The challenge is also temperature. I'm not sure what the gas boilers, but the gas boilers currently connected to radiators.
At the university, we've got everything since 100 years ago to last year. So it's a case of, and even you can pick a building and it's got a mixture of coils inside your handling units plus perimeter radiators, or you could have anything out there depending on the on the building.
So as temperatures rise, the coefficient of performance of the heat pump does drop off. And the CO2 heat pumps are able to maintain those much higher temperatures, but it is at the cost of having a low inlet temperature. So if we're talking central heating, they don't tend to do very well at large volumes. Well, they don't get used for it, basically. You can have cascading systems, so they use a couple of different heat pump gases so that you get the best performance of each one at each stage. But now we're talking about very bespoke, very expensive gear that I doubt would it be vaguely economic for the distributed system that you're talking about here. I would encourage efficiency gains to be looked at really carefully around what heating, but of course then there's a lot of capital cost around that can be quite difficult in the existing building. And a small pellet boiler may be something that is functional. It might not be a containerized system, or it may be a container and it then heats 2 or 3 buildings that are close enough to kind of allow you to plug in, as it were. On a campus style facility, you might have enough space between buildings, because a 20-foot container will do a 64 kilowatt boiler. Two 64 kilowatt boilers, or 3, depending on the amount of fuel storage is in there. And so you can get some pretty significant amounts of heating out from quite small areas. Yeah, it's a massive challenge, I think, for us as a species and as an industry, is that distributed system of heating, because gas is very convenient. It comes in a pipe, you hang a box on the wall, gives lots of energy, and it turns off and on when you want it to. So creatively working around that is going to be a challenge.
Especially when you're in the heart of the CBD and you've got as busy as anything Simon Street, and you don't want to be the one responsible for increased truck numbers in an already congested inner city. Yeah, you can get around that with time of day of delivery or something like that. But yeah, I agree. It's a challenge. Maybe electrification of radiant heat, but then we go back to the same problem of peak loading on the grid and not wanting to increase that. So it's a challenge, isn't it? Okay, thank you.
Thanks, Russell.
Thank you very much, Russell. And I don't see any more questions, Marcus. So
we've worn them all out.
You've worn everyone out, apart from the substantial number of people actually who are still online, which is a testament, I think, to the presenter as well as the content, shall we say.
Thank you.
So thank you very much, Marcus, for a fascinating presentation today. Thanks everyone who has stuck around for an additional almost 45 minutes compared to our schedules. So thank you all very much for that. A quick reminder that we have a couple more webinars next week, one on IoT and one on industrial heat pumps. So we'd welcome you, of course, all to those two. Keep an eye out for them. You can register on our website. And I can't go without another reminder that our conference is on 9, 10, 11 of June. So please, again, check that out. So finally, thank you, Marcus. Thank you, the audience, and still a good number there. I don't know why now they're listening to me. But thanks, everyone, and have a lovely evening. And hopefully we'll see you all next week.
Cool.
So thank you all.
Yep. Where do we go?